Right. Welcome everyone to the 94th meeting of New Directions in Group Theory and Triangulated Categories. We're invited to welcome back Paolo Stellari from the University of Milan. And the title of his talk today is Comparing the Homotopy Categories of dg categories and of A infinity categories.
Yes, so thank you very much for the invitation. It's a great pleasure to give, I think, my third talk in this series, if I'm not the second one. Okay, I thought I also gave one about uniqueness of enhancements, but I might be wrong. Anyway, so thank you very much, and thank you for the people who are attending my presentation. So yeah, so essentially the exposition of today will be about some recent joint work with Alberto Canonaco and Ornaghi. Mattia is also in the audience. And yeah, it's essentially a way to revisit some old work of the three of us, which was previously about the comparison between the homotopy category of dg categories and the one of infinity categories over a field. So actually, while revisiting our work and actually discovering that there was, some issues in the proof related to some the presence in the literature of some mistakes, like not due to us, unfortunately, or fortunately. So that we actually discovered that some of the techniques could be pushed to the boundary, and the results could be extended to dg categories and infinity categories defined over any commutative ring. Okay, so yeah, so I'll try to divide my presentation in three parts. So the first part will be essentially about motivations and setting the stage for the main result. So while discussing motivations, of course, I will take a very personal perspective on the subject. So you can share the same feeling as mine, or you can take different perspectives on this problem of comparing different models, so DG models or infinity models. So my personal viewpoint is actually dictated by the following two observations. So essentially the fact that the observation that any geometrically meaningful, so, and this goes in quotation mark, triangulated category D. So let me lower D. So possess as a higher categorical enhancement. So in the examples we might take in mind, we may keep in mind, so are essentially the usual ones. So I can take so the derived category with any sort of decoration you can take, or the homotopy category with any sort of decoration you might want to take, of where A is an abelian category. And then a question mark can be plus, minus, B, or anti-set. Okay. Or of course, you can get a little bit more into the geometric setting, and you can look at the X, quasi-compact, quasi-separated scheme. Then you might look at the category which does not fit in the previous setting of the derived category of OX modules over X with quasi-coherent cohomology. And again, you can put any decoration here. So complexes can be bounded below, bounded above, bounded everywhere, or unbounded. And you can actually even look at the category of compact objects inside these categories, which are the category of perfect complexes. Or even more geometrically, so you can add additional decoration. So you can take X as above. And then you may look at Z inside X, such that the complement is quasi-compact. And then you might look again at the similar category. Now you take a the derived category of X modules with quasi-coherent cohomology and support it on the closed subset Z with a quasi-compact complement. Or of course, you can take the category of compact objects inside this category. So all of them, they possess higher categorical enhancements. And whenever I consider functors between them, so exact functors, say f from d1 to d2, when d1 di is geometric, so can be lifted if and only if it is of very special time. So in particular, if you are in example 2, and we require that x is also projective, as smooth, then f lifts, sorry. If and only if it's of Fourier-Mukai type. So it's isomorphic to a sort of categorical version of the correspondence at the level of cycle. So it's a push forward composed with a tensorization, composed with a pullback. Okay, so the key issue here is that, triangulated categories of geometric nature can always be lifted, but the exact functors not always. Okay, so there are obstructions to the lifting of the functors. And these two sides of the story, so the one regarding triangulated categories and the one regarding functors, are essentially related to the two themes of this presentation. So the first one about the comparison between the homotopy categories of dg categories and infinity categories, and the second one which concerns an application to the description of internal homes for dg categories. Okay, so but let's start from a quick reminder about the DG category one, okay? Because of course we said that a triangulated category of geometric meaning can be lifted, can be lifted to an higher categorical version, but of course we have several choices for the higher categorical lifting. So the question is now, which higher categorical? And the key point is that I can take a different perspective. So first of all, the first try is given by DG categories. Of course, if I want to enhance a triangulated category, I would like to take pre-triangulated ones. Okay, let me quickly recall the definition, even though I might easily assume that everybody knows the definition. So a DG category is for us a k-linear category C, such that, so let me emphasize that here K is any commutative ring, not just a field, such that, let me write down the two assumptions. So home in C between two objects is a complex. Okay, modulus. And of course, you want the decomposition between, let me write down. So home C between, say, A, B tensor over K with home B, C going to home A, C is a morphism of complexes. Right, and of course, the example to keep in mind here is again a in abelian category. So I can take CDG A to be the category category of complexes in A with morphism given by morphism of complexes. So of course, CDGA is a DG category, a trivial way. And since the morphism of the morphisms in CDGA are complexes, I can just take the homotopy category, H0 of this category, and I get back the homotopy category that I defined before. And of course, if I take suitable quotients in the sense of Drinfeld, then we can get back also D of A, okay, as a quotient of CDGA by the subcategory of acyclic complexes. Okay, so anyway, you can provide and construct all the examples you might want, so there's no particular problem in finding enhancements of all the categories that are we mentioned before. So the key observation is that all the triangulated categories in the first list of examples so yeah, D question mark A question mark A, and then also D question mark QC X, and then also in particular perf X, or the additional decoration, D question mark QC ZX, or perf ZX, they all possess a DG enhancement. So in other words, we can always find a DG category, pre-triangulated one, with an equivalence between the homotopy category of such a pre-triangulated DG category and the given triangulated category in this list. Okay, that's always possible. Okay, now let's talk a little bit about morphism so that we can finally define the object where, the category where all these potential enhancements of these triangulated categories can be compared. So of course, given to DG categories, say C1 and C2. So of course, and then we get a natural notion of DG functor. And of course, as in the previous case, it makes sense to consider H0 of such a F. Right, and of course, if the first item, if F from C1 and C2 is such that, well, first of all, the induced morphism so from home C1 AB home C2 F A F of B is a quasi-iso of complexes, and H0 of F is essentially surjective. Then we say that then F is a quasi-iso. equivalence. And then, yeah, we can actually, at this point, we can actually define the first category we want to consider. So ODG cat. Okay, I should make precise that we work over K, but okay, I will safely ignore this additional predicts down here. So, which I can actually define as simply I can take the category of DG categories. Right, and yeah, I can just invert the quasi-equivalences formally. Okay, I can just take this localization. Okay. So yeah, sometimes I use the shorthand HQE according to the old tradition for this category. And yeah, even though it's this category is indeed defined in terms of localizations, this is since by Tabuada, DGCat as a model structure. So this definition, I mean, gives reason. I mean, motivates the fact that the localization is indeed called the homotopy category, right? Because it's precisely the homotopy category of this model category. Such a model category. Okay, so here's the first main character in this discussion. So it's essentially the first localization that we want to consider. So which is precisely the one involving DG categories. And so the key observation is that inside this localization, we can actually compare the different DG models of the categories that we mentioned before. Okay, so in particular, we know that by a theorem that we proved some years ago with Alberto and Amnon Niemann, whenever we take an abelian category A, then the derived category of A has a unique enhancement for whatever decoration you can add. And having a unique enhancement means precisely what is written up here. So unique means that if I take two such models, then they are actually isomorphic inside the localization HQE that we have actually introduced. So if we see the DG models of a triangulated category of this very special nature inside as objects in the localization, then they are unique in the sense that they are all isomorphic. Okay, that was a conjecture which was open for a few years when we were dealing with the derived category of coherent shifts on a projective scheme, or the bounded derived category of coherent shifts on a similar scheme. Then this conjecture was solved by Lunz and Orlov some years ago, and then generalized several ways up to this one. And actually, I should also add that we have an additional property that says that, moreover, we prove that also DQC X and perf X and unique enhancement. So as soon as we have a good definition for such a localization, we can start comparing the DG models of all these categories, and we discover that they are all the same in the sense that they are all isomorphic inside this localization. Of course, there is also some work in progress, just to advertise. Again, with the three of us, in order to prove that perf ZX and maybe also DQC ZX unique. Okay, but actually this is a different story. Well, so in the geometric setting, we can lift all the categories, and all the models are indeed the same up to isomorphism in such a localization. But as we know, actually, these are not the only models we can take of a geometric category. Indeed, actually, by mirror symmetry, by the homological mirror symmetry conjecture by Kontsevich tells us something more. So it says that, I mean, suggests that actually for a smooth projective variety of a special type, actually one can find actually different models of the same triangulated category. So in other words, we can start with X Calabi-Yau threefold. Okay. So here we are safely assuming a smooth and projective. Okay. Then we can look at the bounded derived category of coherent sheaves, which under these assumptions is nothing but the category of compact objects in this big category. And on the other side, we can get a mirror Calabi-Yau. X check. Now, I mean, so while here we use the complex geometry of X to produce this category, this geometric category by the bounded derived category coherent sheaves. On this other side, we can look at the symplectic geometry of D check, and then we can take the derived category of the Fukaya category of X check. Okay, so here we know that roughly objects are Lagrangian, submanifolds, and morphisms are provided by intersection of Lagrangians. As soon as we can assume that, I mean, they have some transversality property, of course. And now the conjecture says that, I mean, these two categories are must be actually equivalent. Actually, more should be true. So this equivalence should be H0 of some morphism between the enhancements of dbx and the X check. Okay. Of course, we know already that this guy here, I mean, on this side, we can take DG enhancements. By the previous discussion. But on the other side, we know that this guy here, this does not have a natural DG structure, but is actually does have a natural infinity structure. Okay, so in particular, if we look back at X, then X has both a DG model and an infinity model, which is this derived category of the Fukaya category of the mirror of X. Okay, so if we allow ourselves to look at the different models of different nature, then actually we immediately find one. And while we know already that, I mean, on the DG side, actually they are all equivalent. Now we have a natural question, which is actually, what about if we also take infinity models? So can we somehow make sure that even when we allow ourselves to take infinity models of the same geometric category, say EBX, then they are all the same. So they are all isomorphic in a suitable localization of, say the category of infinity categories, okay? So essentially, the whole problem is related to comparing models of triangulated categories, allowing ourselves to take different potential enhancements of the same triangulated category. Okay, so yeah, of course, I don't want to spend time on giving the definition of infinity category. Probably everybody knows. So I just put a slide with the definition. The definition, which is not, as you might immediately spot, 100% correct, because I didn't specify the sign convention. Okay, so asterisk over here has to be made precise, and as we know, signs are important in the theory. But anyway, so for my presentation, we can safely ignore the sign in front. Okay, and of course, whenever we are it's easy to see immediately that dg category are special examples of infinity categories, right? Whenever we assume that all the mi's are 0 when I is greater or equal than 3, okay? But as I explained in the previous example, there are infinity models which are in nature non-DG, okay? So we really need to take them under consideration as well. Okay, and of course, again, another precompiled slide actually about functors. Of course, we can repeat the same story. Whenever we have two infinity categories, A1 and A2, we can actually consider a natural notion of a infinity functor. Natural, so to speak, because it's a sort of weird notion, right? And so, and the condition, the fundamental condition is that this collection of FIs must be compatible with the MIs we defined before, according to this equality. Okay, again, yeah, somehow the signs are not precise in this case. But the key point is that in any case, we can actually look at the H0 of any infinity functor, and then it makes perfect sense to define the notion of quasi-equivalence also in the A infinity context. Right. And so given such a notion of infinity category, the according notion of quasi-equivalence for between infinity categories, we can actually perform the same definition as before. And so we can take the localization of the category of infinity categories. So here there is a question mark, which contrary to the previous one will not be ignored. So we have to address the meaning of this question mark later on, right? And actually one maybe interesting observation is that it's well known actually. It's well known that that indeed a infinity cat does not have a model structure with limits and co-limits actually. So it's we should think of this object really as a localization, not as a homotopy category of a given model category.
I have a question.
Sure.
So just like a sanity check. So the quasi-equivalences here in this definition, do they depend in any way? Do they depend on the model structure?
No, they don't depend. There is no model structure here. Eh? So there is just the definition that I mean, as was somehow indicated in this previous slide. So I can take an infinity functor, and again, since anyway, the complex of the morphisms into the two infinity categories form complexes. Okay, just look at M1. Okay.
Yeah. Sorry.
Then I can look at the induced map. It's exactly the same definition as before. I can look at the induced map between the complex isomorphism, and I just require that they are quasi-isomorphism. And then I can look at the H0, and then we can require that they are essentially surjective.
Thank you.
Okay. can actually perform the same definition. And yeah, and then I just localize. Okay, then of course you can complain a little bit. Actually, you can complain a little bit because I mean, why? I mean, this localization should be a category. Okay, so if I take it, of course, quasi-equivalence they don't form. Sorry. So it's a weird localization. It's not a multiplicative system actually. So in particular, a priori to define such a localization should enlarge a little bit the universe, make sense of this category. But then, I mean, we will see that, I mean, this category, after all, is equivalent to the previous one, which is obtained from the model structure. So it will turn out to be a category in the proper sense. I mean, not a posteriori. Anyway, so I can always take this localization, and you can complain a little bit if you're very much concerned about some foundational questions, whether this is a category in a given universe, okay? And so, but we will see, I mean, it's a posteriori, the answer is yes. And right, so the key point for us is that the comparison between the different models of given triangulated categories must take place in O infinity cat. Okay, and now here actually I leave the question mark. Okay, and discuss the question mark a little bit later. Okay, must take place there because we know that the same given triangulated category may have a DG enhancement, but also an infinity one. And so, and after all, the natural place where they must be compared, so it's precisely such a localization. And of course, actually, so the second question is theorem 1. So the one concerning uniqueness of enhancements. Extends. So the question is, extend to A infinity models. So can we prove that the category which were in the list that I mentioned at the beginning, they do have a unique model, not only at the DG level, but also at the infinity level, okay? In particular, if you can answer in the positive, and the answer will be yes, of course, after all, after we state and prove our theorem, then in particular, also the equivalence, which should conjecturally relate the bounded derived category of coefficients on a given Calabi-Yau threefold and the derived category of the mirror one. So it's actually of a purely triangulated level, because whenever I can find a triangulated equivalence, then I can certainly replace it by one, which can be lifted at the level of the localization of infinity categories. If we can prove, of course, such a result as a truth. So let me write it here as a consequence. If the answer is positive, then the equivalence from homological mirror symmetry that I mentioned before is of purely triangulated nature. So in other words, I don't need to construct an infinity quasi-equivalence between these the enhancements of these two categories. I can just construct the triangulated exact equivalence between the homotopy category of them, so the bounded derived category and the derived category of Fukaya. And then by the uniqueness of enhancements, I know that I can lift it to a quasi-equivalence or a chain of quasi-equivalence between the given models. Questions so far? Okay, so now the idea is that now I would like to move to the statement of our results, the results with Alberto and Mattia, and give a little bit of a sketch of the proof and possibly move to the application. Okay, now, so first of all, we should make clear should clarify the meaning of question marks in infinity cut question marks above. And the key point is that infinity categories have different notions of unit. So let me remind. I mean, at least the two main ones that which are part of the which appear in the result, and then a third one which is interesting as well. So the first notion is the one of strict unit. So it means that for any object in A, okay, A is an infinity category. Category, there is actually the identity, okay, which is a morphism closed of degree 0, such that if I take M2 between any guy and the identity, then this is the same as, say, A prime tensor blah, and this is indeed the identity in home. Sorry, home A prime. Okay, and of course we want also to require that if I look at higher MIs and I take a bunch of morphisms, and at some point the identity appears. So here, this must be 0 for I greater or equal than 3. Okay, and this comes, of course, with it comes. We also have notion of functors between strictly unital infinity categories, and all together they form the category A infinity, what I will denote A infinity cut. So it means that the question mark is just the empty set. There is no requirement. Okay. And yes, and then I can actually, as people know from doing mirror symmetry, these categories are somehow useless. So you have to relax a little bit the notion. So then there are various notion of being unital. The one we will adopt is due to Manziuk Lyubashenko actually, and their school actually, and that says the following. So it's a very flexible notion. So for any object there exists an EA, morphism between A itself, which is closed of degree 0, which represents the identity, say, id A in home, sorry, in H0, sorry, of the infinity category A. And then we have two additional conditions, plus, let me write, plus you want that M2 of blah tensor with AA and M2 AI tensor blah, they are homotopy to the identity. It's not just an equality, but you ask for an homotopy. And this form a category which we will denote by A infinity cat U. Okay? And those are the two, essentially the two categories which we will be interested in. This one and those that actually have a unit in this weaker form. Of course, we can define other notions of unit. So in particular, the weaker one is the notion of cohomological unit. And simply request in this case requires that H0 of the infinity category is the category, so as a unit for all elements. Okay, and in this case, the category which we will form is indeed this one. So, I mean, we should note that in general, so if K is a commutative ring, then you have the inclusion. Unital, and then you get into infinity cat. See, so you should not expect you should not expect I mean them to be general. Functors are not equivalencies. Okay, and the first observation is that probably there are other notions of unit which of unit which we will ignore in this presentation. One is due to Kontsevich and Seibelman. And the other one is due to Fukaya. So, but there are very nice results by Lyubashenko, and they show that essentially all these, if you just look at the category and you forget about the functors, these notions they are all coincide with the notion of unital infinity categories, which is mentioned over here. Okay, so in a sense we can ignore them because the unit in their sense coincides essentially with the one defined by before. Okay. Questions so far? Okay, so these are essentially the categories which we want to consider. Now let's go to the statement of our result, and the theorem is the one that is written up here. So it essentially says that, I mean, of course, we have this inclusion that was mentioned in the previous slide, but we already know that dg categories are special examples of infinity categories. Of course, I mean, the functors are only faithful, so this inclusion here has to be taken with some care. Not a fully faithful functor, it's just faithful, because I mean, again, between infinity categories we can have between dg categories we can have infinity functors which are not dg. Okay, and the same is true when we compare these two guys. Okay, we can have between two strictly unital infinity categories, we can have functors which are unital but not strictly unital. Okay, so these are only faithful functors. But the key point is that if when we look at the localizations, then these inclusions they induce equivalencies, okay, between the three categories which are mentioned over here. Okay. And the funny fact is actually that, I mean, they can be compared also to another very nice and very useful category. I'll comment a little bit later, which is the one mentioned down here. Okay, maybe we can, I can spend a little bit of time. Spend a bit of time defining the latter category. So let's see. First of all, yeah, there are, so the category has at least a couple of decorations that must be explained. So first of all, there is this HP down here, and then there is this relation that appears in the quotient. Okay, so let's see. So yeah, so let me just remind you that an infinity category is H projective if the uncomplexes, if it's, sorry, complexes are such. And yeah, let me mention that, I mean, of course, if K is a field, then this is no condition. Okay, so it's not an additional requirement. And then we can set so A infinity cat U HP inside A infinity cat U to be the fully faithful functor, a full subcategory consisting of H projective, unital, infinity category. Okay, and this clarifies the first decoration in the category which appears. And yeah, the second one is about the double tilde. And yeah, and it goes like this. So now we are in business to define this category here. Is the category whose objects same as those of A infinity cat U, and for morphisms, so not for morphism, so we do the following. So we take A infinity cat U HP A prime. We set it to be the same as functors. Sorry. Oops. Where we say that f and g from A to A prime to H projective infinity categories seen as objects in the category of functors. Sorry. U A prime are such that F is twiddle twiddle G, if and only if they are isomorphic. In H0 fund. Cut U. Okay, so that's the additional category that we can define, which is actually a very useful one in the sense that so it's the one that will allow us to interpret also the composition between in the internal OMS in a very natural way. Okay, so questions about the statement. Okay, so maybe I can very quickly sketch the idea between for the comparison. Here it is the additional comparison I want to discuss. So I'll try to be very brief since I want to move to the applications. So and the point is that actually, so the idea is to realize an adjunction between the inclusion of a dgcat inside infinity cat. Again, you should be careful because it's not a fully faithful functor. And so the construction of the left adjoint is the standard one. So you start from an infinity category. So let's restrict for a second to the case of strictly unital ones. And then we perform two classical construction. So the bar construction, okay, which essentially is a tensor construction. And then we again do a tensor construction, getting the additional co-bar construction applied to D, to B infinity. And this defines a functor actually. Okay, so it's a double tensor construction. So here is the precise definition of omega, and up here the precise definition of B infinity. And of course, we are not done yet because this, if we apply UN, okay, to a strict unital infinity category, we don't quite get a DG category. So it's a DG category with a cohomological or unital flavor. It's not strictly unital, so it's not a DG category in the sense that we mentioned at the very beginning. So we have to deal with an additional operation. So essentially, we take the construction given by the bar and co-bar construction. We take the augmentation. So we add an identity for any object, and then we quotient by some DG ideal. Okay, and the DG ideal is very shortly described in these terms. So is the smallest one, such that the infinity functor which we obtain as a composition gains the property of being strictly unital. Okay, and this actually provides an adjunction, which is actually a Dwyer kind of adjunction. So also quasi-equivalences are preserved on both sides, and in particular, due to we can prove the following theorem say 3. As a consequence of this Dwyer-Kahn adjunction that says that the above induces an equivalence. So I'll write in comment. Sorry. So an infinity equivalence between these two categories, which should be where maybe let me write it here. O dg cat infinity and O infinity cat infinity are infinity categorical enhancements of the localizations. so obtained by the nerve construction. So that's the standard thing. And let me just comment that remark. So actually, I mean, theorem 3, which I'll again, let me display it again. So it's essentially about the existence of an infinity equivalence between the enhancements of this guy. Okay, so sorry. Okay, so it's indeed about the existence of an infinity categorical equivalence between these two guys. So such a theorem is indeed generalized. The work of Paskalev over any commutative ring. And in particular, it provides a proof of the same statement by O and Lee Tanaka. So actually, their statement is indeed the same as this one, where I mean they put an additional decoration up here. So here they want really have unital infinity categories. We cannot prove it at the moment in this generality. But we should also remark that, I mean, their result is about infinity categories and dg categories linear over any commutative ring. So it's slightly more general than Pascal one. And but the key point is that the proof which is contained in the preprint contains a gap. So and somehow that's so our work is also a way to repair a little bit such a statement, provide a complete proof of the result. Questions?
Yeah, can you repeat what you just said? Your
theorem. So this theorem appears. So the claim is that this theorem, with the additional decoration of, if you add a U here,
yeah,
okay, was a theorem, and you assume that all the categories are linear over a commutative ring, was a theorem in a paper by O and Lee Tanaka.
That had a mistake.
But unfortunately, it contains a gap or a mistake depending on your viewpoint, actually. So actually the proof doesn't work.
Right.
So the theorem was repaired by Paskalev over, I mean, when the categories are linear over a field. So that's the first, what I'm saying up here. Okay, so the theorem was proved exactly in the same generality as us. So with no U up here, no U. So just looking at strictly unital infinity categories. But I mean, for categories which are linear over a field. Okay. So Pascal has proved this theorem under these two assumptions, that you work with strictly unital infinity categories, but linear, which are linear over a field. Our result is essentially a generalization of your result and does a proof of O and Lee Tanaka theorem.
Right.
Okay, assuming that you're working with categories which are strictly unital and not unital.
Yeah, thank you. Yeah, that was what I wanted to know. I wanted to know if that gap had been fixed before your paper by anybody else.
No, it had been fixed before, but only over a field, actually.
Yeah, thank you.
So in particular, it has been fixed now by our paper over any commutative ring. So yeah, thank you for the question. Okay, so yeah, can I just take 5 minutes to discuss the last?
Yes, please, no problem. Take as long as
the last applications. So the applications now. Okay, sorry. The applications are essentially about the internal OMS, and I planned also to say something about the application of this new description of internal OMS to description of the Oxford complex of infinity categories, but I'm not sure I'll have time to do it. So yeah, the key point is that I mean we know by the work of Toen that I mean essentially, so ODG cat is a closed monoidal, sorry, symmetric monoidal category. So meaning essentially that we can define a derived tensor product of, so that's the derived tensor product. And this guy has a right adjoint, which is, as usual, denoted like this. So this is a DG category of internal ohms. Okay. And yeah, by the work of Toen, then also, I mean, reinterpreted by Canonaco and myself later on. So we know that an explicit description. So in other words, we know that, I mean, if you want to compute a ROM between C and D, where C and D are DG categories, then this is nothing but given by H projective bimodules. Okay. Now I hope that the op goes in the correct direction. So, and I take the H projective DG bimodules, which are right quasi-representable, meaning that if I look at the bimodule and I interpret it as a functor, then the image of the functor must be contained in the essential image of the Yoneda functor of T. Okay, so that's the meaning of this right quasi-representable. And in particular, so yeah, in morphism, see, no, O DG cat, the D are actually in natural bijection with the isomorphism class of H0 of this internal OM. So in other words, I can really interpret morphisms in the localization of DG categories in terms of such bimodules, okay, up to taking isomorphism class in H0. Okay, but the key point is that, I mean, before all this work has been done, there was this beautiful claim or, I mean, conjecture, I don't know, by Kontsevich. It's a really beautiful idea, actually, I have to say. Then revisited also by Keller. That says the following: that let A1 and A2 be DG categories, such that so A1 is H projective. But as we said, if we work over a field, as I mentioned before, this is no condition. So requiring that the DG category is projective is automatic. And plus, there is an additional requirement that the unit PEP from K to home, say, A1, AA admits a retraction. The morphism of complexes. This is for any A1. Then the DG category which we already encountered before. So I can take Fun A infinity cut, and now I plug inside my two dg categories. So this is the dg category consisting of A infinity functors, strictly unital A infinity functor between A1 and A2 is the category of internal ons between A1 and A2. That's a beautiful idea. So first of all, I mean, that was so it's a beautiful idea because first of all, it comes well before the amazing work by Toen, and so it was really a vision at that time, I think. And also, I mean, it's a beautiful idea because it gives you a very pretty description of morphism in HQE, essentially. So in the localization, the homotopy category of DG category. So they can really be realized as infinity functors. So as functors in a proper sense, okay? Not by modules, not functors realized by module, but actually infinity functors, okay? It's a beautiful idea. So I have to say that, I mean, a comment. So I'll try to finish in a very short while, don't worry. So a comment.
You can take as long as you want, it's fine.
No, but I'll try to be. So this was proved by Faonte and so when K was a field. Okay, there is a little issue here. So I mean, the proof of Faonte contains a mistake. So our proof, I believe, is correct, but it is based on results by other people that are, I mean, are not completely correct. Okay, okay. So this is so. In the sense that the proof, our proof is correct. The proof in the paper is correct, but I mean, we use the results which are incorrect. Okay, proven by other people. So in other words, I mean, we felt the necessity to try to put a patch to such a story, and indeed, what we can get is indeed a final statement that says that whenever we take 3DG categories, now linear over any commutative ring, okay, so it's in full generality. Then we get, I mean, the following natural bijection, which simply says that, I mean, the presence of such a bijection simply means that this guy here is the category of internal ons. So it's the right adjoint in HQE to the tensor, derived tensor product. Okay, so we have a natural bijection which realizes Kuhn and infinity cat U A2 HP A3 as the internal on, as the category of internal on. Now you have to be careful, okay, because so here you see that, I mean, there are again some decorations that you might be not happy with. So first of all, is this fact here that, I mean, there is a U here, okay, and there is this H projective resolution, okay, but you should not be worried. So we know how to define all of this, okay. So in particular, I would also comment that again we get a bijection between the morphisms in ODG cat and the isomorphism graph in H0 of this DG category. Okay, so I have to comment a little bit about this decoration very briefly, and then, but let me just mention that actually, I mean, this description over here makes the bijection automatically compatible with the compositions in the first and the second argument, so in A1 and A2. Okay, so in the comments, the final comments are the following. First of all, so the theorem implies the conjecture, AK conjecture. Okay, you remember that in the conjecture, the first category is assumed to be H projective. So taking the projective resolution doesn't do anything, essentially. And furthermore, I mean, so whenever these, so the difference between the conjecture and our result is that, as you can see here, the category of internal HOMs is realized as a category of strictly unital infinity functors. While here we are taking the category of unital infinity functors, okay? But it's not hard to observe that, I mean, if this additional condition is satisfied and A1 is H projective, then automatically this category here is equivalent to is isomorphic in the localization to this one, okay? So they really are the same, okay? So in particular, fun infinity cat U is isomorphic to fun infinity cat if the first category is H projective and the additional condition on the identity morphism is satisfied. So if you want, our result is not only a proof of the conjecture, but it's a proof of a much more general version of the conjecture, okay? So we don't need to assume that, I mean, the category is H projective, and we don't need to assume that, I mean, you have this retraction of the identity morphism, okay? So we still have a description of the internal HOM in terms of A infinity functors, now unital ones, where you take an H projective resolution of the first one, actually, okay? When the two conditions in the Kontsevich and Keller claim are satisfied, then you get back the result. And let me also mention that, I mean, that's probably trivial for experts, but the compatibility with compositions was somehow an open question in Twine's paper. And you have to, you can easily guess why, actually, because if you look at the internal HOM described as H projective modules, bimodules, with some additional requirement on the image, so this requires the representable condition, then you can easily imagine that, I mean, the composition in the first category will be replaced by a sort of convolution between bimodules. Okay, and then checking that all the bijections are compatible becomes a little bit messy. Okay, so you don't really want to deal with such a computations. But as soon as you replace the internal HOMs by a category of real functors, then I mean the composition on the first category here, so becomes essentially composition of A infinity functors on the other side. So you have composition on this side and composition of functors on the other side, and it's not hard to check that. I mean, the two natural notion of composition, they are compatible with the bijections with those structures. Okay, sorry for being over time. I'm really very sorry, but yeah. So if you have any question, please ask.
Thank you very much, Paolo. Let's all give the speaker a round of applause. Okay, if you have any questions for Paolo, you can ask them now.
I think there is something in the chat. Ah, no, okay. Oh. Thank. So, by the way, hi David. It's a long time we don't meet actually.
Was the original intention of, I mean, the Kontsevich-Keller conjecture, was it supposed to have any bearing on the homological mirror symmetry?
I'm not quite sure it was meant to have a direct. I mean, I'm not an expert in homological mirror symmetry, I have to confess. So I know very little, but I don't think it was actually meant to be directly applicable to homological mirror symmetry. I think it was just a beautiful insight on what it was going on. Of course, it has also beautiful applications because so essentially, I mean, so if you take a dg category, there is a very nice application of the description of internal OMS given by Toen in Toen's paper in terms of the description of the Hochschild complex. Okay, and so the Hochschild complex is nothing but the OMS in the category of internal OMS between the two dg categories, between the identity functors. Okay, and so if you look at this specific incarnation of the internal OMS which is given in Toen's paper, it's not clear at all how to generalize these to infinity categories. But now, if you know that the internal OM is a category of functors between DG categories, you can immediately replace the DG categories with the infinity categories. Okay, and now you can look at the OMs between in the functor category between A and itself, between the identity functors, and then this would define for you a Hochschild complex of 4 infinity categories. So that's probably one application which was probably in the mind of these people, actually. And so, and actually it was made precise. I mean, given this theorem, actually, it's and also our theorem, our previous theorem, actually the one about the localization. So it was made precise by Faonte and also by O and Litanaka. So they essentially extend the theory of Hochschild complex to infinity categories in this sense, and yeah, and you can prove exactly the same results that Toen proves for the Hochschild complex in this new setting. So I think that's probably one of the most striking application, which was probably also envisioned by these two guys. But
That's okay. So the homological mirror symmetry remains open.
so the only application that I can see of these two theorems we prove to homological mirror symmetry is what I mentioned before. So a priori, you should look at, so to realize homological mirror symmetry, you should look at an A infinity equivalence or a sequence of A infinity equivalence between the DG enhancements of DBCO and the enhancement of the Fukaya category. But I mean, if you combine our previous theorem with our uniqueness of enhancements theorem, then it's just a triangulated one. It's enough to exhibit an exact triangulated equivalence, and then that would provide for you the A infinity equivalence for free, essentially. Yeah, that's the only application that I can see.
Thank you.
You're welcome.
Any other questions? Oh, Volodymyr Lubashenko was in the audience. Hello, Volodymyr. I hadn't noticed you before.
Yeah.
Okay.
Okay. So thank you very much.
Just one. Yeah, sorry, Volodymyr, were you going to say something?
Thank you for the nice talk.
Thank you very much. So I should also point out that, I mean, the proof of this last theorem relies very much on the beautiful work by Lubashenko and co-authors. So, so it's an amazing piece of hard mathematics, very, very hard actually. So, yeah.
Okay. Yeah, thank you all for coming. We'll actually have Bertrand Toen as our speaker in the 100th meeting of this seminar.
Okay.
In a couple of months. Okay, thank you. Let's thank Paolo once again.
Thank you very much. Thank you, everybody.
Okay, bye-bye.
See you soon.
Yeah, see you soon. Bye-bye.